Physical science. This is our last section in chapter 25, and it's all about volcanoes. So the main idea is that they form when molten rock rises from deep within the earth and erupts from a crack or a fissure or some type of fault or weak point in the crust. So volcano formation. Melting can occur in the asthenosphere. Molten or liquid rocks stored inside Earth is called magma. Magma is less dense than surrounding rocks, which is why it rises. It's more buoyant. Rising magma may reach Earth's surface if pressure conditions allow, and the rock has conduits through which it can flow. A volcano is a feature that forms when magma reaches Earth's surface and erupts as either lava or ash. Volcanic eruptions occur where plates separate along a mid-ocean ridge or where plates collide along a subduction zone, as shown in this map. Convergent plate boundaries. Most of Earth's volcanoes are located along plate boundaries that surround the Pacific Ocean, and it's called the Ring of Fire. Here, volcanoes from where tectonic plates collide along subduction zones. Volcanoes in the northwestern U.S. and Alaska form along subduction zones within the Ring of Fire. So if you remember, early on in the chapter, I said, it's not gonna go away. Well, here we go. Divergent plate boundaries. Volcanic activity occurs along divergent plate boundaries, and most of this activity goes unnoticed because it occurs underwater along mid-ocean ridges. There are places where volcanic activity occurs on land due to divergence, such as the East African Rift Valley. So if it's underwater, we call it a moor in mid-ocean ridge. If it happens on continental crust where there's no ocean, we call it a rift valley. Make sure you understand the difference. Hotspots. These are areas of volcanic activity where magma moves towards the surface in large balloon-like plumes. Scientists hypothesize that these plumes originate near the core mantle boundary. Hotspots are stationary, unlike the plates that move above them.
Another area that is mapped in detail lies in the middle of the Pacific, the island chain of Hawaii. At the eastern end of the chain lies the Big Island, where Mauna Loa, the world's biggest volcano, rises 13,500 feet above sea level. Why is the Big Island so big? One theory is that it sits over a hotspot, a place where hot, buoyant magma rises toward the surface from deep within the earth. As the magma punches through the surface, it creates the island. Even today, the Big Island is very active. Another volcano on the flanks of Mauna Loa, called Kilauea, has been erupting for the last 25 years. Above the waves, the Big Island is impressive. But when we lower the sea level, its true size is revealed. The Big Island itself is big, but without the water, the island above the surface is dwarfed by the vast underwater cliffs. Measured from its base, this is the biggest mountain on Earth, rising 4,000 feet higher than Mount Everest. Looking down on the Big Island, as it's never been seen before, the ridges of its massive volcanoes are lost next to the rest of the mountain, normally hidden by the ocean. But we're not just visiting the Big Island because of its size. The Hawaiian Islands and the surrounding seafloor have been mapped so accurately that John Smith from the Hawaii Undersea Research Lab can use his computer to fly around the islands, above and below the water. And these surveys reveal a small underwater volcano, a seamount.
Here we have Loihi Seamount. It's an active volcano off of the Big Island of Hawaii. It's about 20 miles or so off of the southeast side of the Big Island.
The Loihi volcano lies 3,000 feet below the surface, but it's just as active as the volcanoes above the water. Magma below the seabed creates shimmering columns of hot water. Scientists have monitored Loihi since it was discovered in 1955, and they found that it's slowly growing toward the surface. It seems Loihi is being created by the same hotspot that gave birth to the Big Island. The Big Island is drifting off the hotspot, and Loihi may eventually take its place, growing larger until it breaks the surface as the newest Hawaiian island.
Hi, I'm Diana, and you're watching Physics Girl. So, I grew up in Hawaii, on the island of Kauai, which is the oldest of the main islands, the wettest, the greenest, the most beautiful. It had no nightlife. There were 22 kids in my graduating class. I digress. So the Hawaiian Islands are geologically weird. They're formed by volcanoes, we know that. But wait, scrap that. They're formed by volcano. Just one. It's like an upside-down chocolate kiss conveyor belt. There's a hot spot that forms the volcano, and then the plates move over the top, making the islands one by one. Bloop, bloop, bloop. Now you know. So, one of my childhood friends, Noah Randolph Flagg, became a geologist at UC Berkeley. And when we were back home over the holidays, we went for a hike and got talking about how unusual the formation of the Hawaiian Islands is. It all started with a mystery.
World War II, the U.S. military was looking for Japanese submarines in the Pacific. And the way they did that is they'd lower a magnet off the side of the boat, and the magnet would get pulled down if there was a metal submarine under there.
The military mostly used planes with these magnetic contraptions, but scientists later adapted the technology for boats.
And, well, presumably they saw some submarines. I don't know about that, but what they also saw was the magnet would go up and down sort of periodically on the ocean floor. Sometimes it would pull really hard, and sometimes it wouldn't pull very hard. Do you have a thought on why?
This was the mystery. This magnetic contraption was made in wartime to search for submarines underwater, but something else was pulling on it? Something unidentified and deep underwater.
I'm gonna guess that it had to do with how much magma was close to the surface of the ground, and because there's more iron, I'm guessing, in that rock, then it pulled harder?
You're totally right. It's about well, you're totally...
Noah's brother Jeremy, who's also a geologist, just told me that I'm not totally right.
You're totally right that it's about the iron
Jeremy!
in the rock. If you imagine a molten rock as being a bunch of little magnets floating around, what direction do you think those magnets would align?
I would imagine that they would align along the magnetic field lines.
Excellent. Okay, so we have all of these magnets in the molten rock that align with the Earth's magnetic field.
Yeah.
And then they freeze and they're stuck there.
Oh, okay, go on.
And the Earth's magnetic field would reverse. And so what they were seeing was these stripes was the reversals of the Earth's magnetic field. And
What?
yeah.
What?
Yeah. And the other thing they noticed is across the Pacific, it's symmetrical. It looks almost like a barcode.
Yeah.
But it's a symmetrical barcode. And they're like, well, that means that all of that crust is being produced in the same place.
And this is how we learned that the Earth even has plates. It's the number one thing you learn in Earth science.
Tectonic plates!
And we figured it out because these lines of little magnets aligned with Earth's magnetic field as it flipped over millions of years and then was frozen into the rock. Amazing! The vast majority of volcanic activity on Earth occurs along plate lines. And that makes sense, because if you're gonna spill your guts, you're more likely to do it along a seam. But there's one glaring exception.
Hawaii is dead in the middle of a plate. Plate tectonics doesn't explain a place like Hawaii. So that's sort of a problem. So what people call on is this theory called mantle plume theory. The idea, right, is thermal convection is hot stuff is less dense, cold stuff is more dense, cold stuff goes down, hot stuff comes up. So you imagine convection as the boiling of water on your stovetop, right? In the Earth, that convection is happening in solid rock. Yeah, so we're talking about motion of solid rock, right? Because at those time scales and at those length scales, the ground, the solid rock that you feel is as viscous as the maple syrup that you're pouring.
That's amazing. So this is rock moving through rock.
Yeah.
Wow.
So if you scale things the way that we think that they scale, it looks like a lava lamp, right? You have some hot stuff rising, and it starts with a big blob, and then there's this long, skinny tail behind it. The same physics happens in, like, nuclear bombs, right? You know, the mushroom cloud is the same idea, right? There's that big buoyant plume, and then the tail, the skinny tail behind. So the idea is that Hawaii and the Hawaiian Islands and these other hotspot volcanoes are that tail.
Hold on. So, this mantle plume theory says that an unusual hotspot like Hawaii is just the tail end of that blob shape of solid rock rising through solid rock. That's it.
So then you might ask, well, where's the bubble? Where's the bubble? People have argued is that those bubbles are these things called flood basalts. This is good, I promise. This huge bubble just explodes onto the surface, and so most of Siberia is covered in lava flows, and most of India is covered in lava flows. Individual lava flows that are hundreds and hundreds of feet tall that cover an entire country.
Wow.
And
so that was, I mean,
that's
like,
the thought is that was the bubble.
Bubble exploding?
Yeah,
or?
That's that bubble exploding into the surface. This is the tail and the head.
Yeah. And then as the head gets higher and higher, the pressure is released. And that means that the solid rock is going to start turning from a solid into a liquid.
Yeah, and so that's what we call magma. And
so
the reason
have we ever seen anything like that happen?
Never.
Would it be an incredibly violent event?
Well, this gets good. There have been many extinctions in Earth history, and many of them correspond with when we think these bubbles explode to the surface. So the most recent one was 40 million years ago, and it was tiny, like a thousandth of the size of some of these.
Yeah.
But the largest extinction in Earth history, the Perma-Triassic, happens during the largest flood basalt.
So yeah, let's hope that doesn't happen anytime soon. Okay, so recap. The Hawaiian Islands are forming on a hotspot that's the result of one of these mantle plumes popping up through the crust like a hot pimple. You're welcome. And this might tell us something about the geology on the planet Mars.
We think that plate tectonics is not happening on Mars, but we think that probably mantle plumes are, and that's why we have these giant volcanoes like Olympus Mons.
Okay.
And part of why Olympus Mons is so big is because there's not plate tectonics, right? So stuff's sort of piling up in the same place. But in Hawaii, because...
This is part 1 of 25.4, Please continue watching 25.4 Part 2.